Hi guys, and welcome to this Houdini video tutorial. Today we're going to take a little look at using RBDs or rigid body dynamics and how to get that set up using their shelf tools, and then in further parts we'll have a look at building a lot of the node networks ourselves and start to understand a lot of the inner workings of how we actually work with simulations in Houdini. Okay, so let's get started. So I'm just in a fresh Houdini scene, absolutely nothing in it at all to begin with. And when dealing with rigid bodies, there's a couple of tabs that you want to be aware of. Firstly, you have a rigid bodies tab itself up here on our top right hand side, and we also have a collisions tab. Both of them are dealing with rigid body objects. This collisions tab is telling that you will have a non-deforming object to collide against. And the cool thing about the shelf tools is that it will build large proponents of your node networks for you, and you can use it to kind of really start to understand what's going on with Houdini. So I'm going to create a ground plane to begin with, and it will automatically create a couple of nodes for us, and into our scene we can actually see our ground plane object. So let's have a look at what's particularly happened. First of all, we've got a geometry node called ground plane object, and in there we have an object merge node that's bringing in this ground plane display node from within our Autodop network. The Autodop network is just a dynamics operator network called Autodop. And if we dive inside, we can see what type of nodes have been created for us. Firstly, we have our ground plane object. That is what the geometry object is merging into that, so we see it. We have that being solved by a static solver, and then it's getting gravity applied to the simulation, and then it's being displayed to us down here. So if we want to kind of add in a rigid body object, we can do that very simply. We're going to type tab and drop in a geometry node and dive inside and delete out the file node. I'm instead going to bring in some geometry, and luckily within Houdini there's some really nice test geometry objects. So I'm going to work with the test geometry pig head, just for an interesting object to particularly work with. So here's what we have, our normal geometry. It's just polygons at the minute. Again, polygons have no knowledge of mass or weight or any consistency when it comes to dealing with collisions. We need to tell this particular object to become a rigid body object. So if we go up to our rigid bodies tab, we can click on our first object, this RBD object, with it selected, and again it will automatically do a lot of things for us. And to kind of see what it's actually done, I'm going to raise this object in the Y direction and maybe give it some rotation as well. And if I press play by pressing up on the keyboard, we'll actually get our simulated object actually working. The other kind of keyframe will be controlling up, or if you're working on an Apple, commanding up will go back to our first frame and give us the ability to jump back to the beginning of our sim and press play using the up. So you'll be using that keyboard shortcut of commanding up or controlling up all the time. So let's have a look quickly again what's particularly happened. So let's dive inside our Geo1 node and see what's happened here. Firstly, we have a few things going on. Firstly, we have a rest node, which is essentially telling Houdini where this object originally was in world space. Then we have an assemble node, which is packing our geometry. We can kind of talk about why we want to use packed geometry in a bit as well. and it's being given a name attribute, and if we click on our information we can actually see all of our details that is being added here. So we have a name string attribute, our point position, as well as a path. We'll also talk what's happened here, because you can see that with this pig head, which is very clearly lots of polygons, it actually says that there's actually only one polygon, one point primitive here. So we'll talk about what's actually happening. And then that's being fed into our simulation, and this DOP import is actually bringing the simulated object back out of Dynamics again. So it's fetching the geometry from the DOP network after it's been simulated. So it's a bit confusing sometimes that this is actually connected up, but even if it's unconnected, it will generally still bring in that geometry. The reason it's not at the minute is because the Dynamics network is actually sourcing it from this DOP import as to what is actually being brought into Dynamics. So what is visualized is what the simulation is bringing in. So at the beginning it does need to kind of be visualized itself. Into our Autodop network we can dive inside, and sometimes these nodes will be placed on top of one another. If you just press L, your network will be laid out in a nice fashion and you can start to analyze what's happened. Firstly, we've brought in an RBD packed object that is pointing to that surface operator, which is our packed primitives there. And if you middle mouse button click, it will evaluate the expression within this node itself. It's then being fed into a rigid body solver, which is being solved using Bullet. Houdini has multiple ways to solve rigid bodies, but by far the fastest is going to be Bullet itself. And again, if we press play, our simulation is playing out. One thing to bear in mind is the way that Houdini is actually calculating all of the collisions isn't with this geometry. Bullet does not use the polygons and primitives that you actually expect that it might to actually calculate its collisions. And the way that you see that is by selecting your packed geometry object and then going down until you see bullet data, and then turning on show guide geometry. And sometimes you might have to turn off the display geometry for the actual object, which is here, to see this. So what has happened is it's using this geometry representation of convex hull. And what convex geometry actually does is it basically kind of wraps it in paper almost. So if you were kind of having a very elaborate Christmas present, it was wrapping that round and leaving no kind of indentations in the object itself. So if we compare this to our original geometry, there would be nothing that would be able to collide with this part, this dipped in part of the pig's neck. Similarly, this part within the mouth, because to simplify collisions down, the convex hull method does not allow for that area to be calculated. You can see that it just all gets smoothed out with this, this big polygon plane. But that makes solving for collisions very, very simple, and we actually get relatively quick feedback. There are other methods of calculating collisions, but they can be more expensive or less expensive depending on what you choose. For instance, you could choose a sphere collision object, and if we press play now, it will just drop, but if we give it some initial velocity perhaps of 2, it will kind of go off to the side, and because it's a sphere it will actually roll. But obviously our geometry isn't spherical, so that if I turn off this show guide geometry, we actually get some really strange movement, but it's actually been solved very, very quickly because it's just using primitive spheres. So where this might come in handy is if you have stuff in the background, something really, really small that you just need to solve a lot of, but don't want to kind of invest a huge amount of time in complex simulation. That can also work, but you don't want it so that the audience is then going to notice these spinning kind of objects, basically. So yeah, there's a few things that you can choose here. One of the more expensive choices is to use concave. And if I kind of toggle that on and show the guy geometry, you actually don't see much change until I turn off the display geometry. You can actually see that this representation is very, very close to our original pig head geometry. And if I press play, we'll actually get some very, very accurate movement and kind of tilting of the pig head because of its collision geometry. Just bear in mind that this will take much longer to simulate, especially if you have a heavy scene than a convex hull. So just bear that in mind. But any RBD object and any collision object that you're working with in simulation has a representation of it that it's using for simulation. This is very, very different to what is actually being displayed. So you have to really pay attention to how that's actually working. So that's how we kind of set up an RBD packed object within Houdini using some shelf tools. Let's have a look at how to turn this into a breakable object. So first I'm going to strip out these nodes here in terms of our simulation. And I'm also going to delete out our geometry one, which would be our pig head geometry. I'm going to drop down a new geometry and a new pig head here. And this time, to actually shatter this particular mesh, there's a really nice kind of shelf tool that actually does that for us. It's on our model tab up here on the top left, and we want to use the shatter tool here. And it's dropped in a few nodes here for us, an iso offset, a scatter, and a Voronoi fracture. And on our Voronoi fracture, if we visualize our pieces, we can see that our pig head has indeed been cut up into multiple pieces. And the multiple pieces is based on the amount of points within this scatter. So if there's 100 points, we'll have 100 different pieces. And the visualized pieces is just really nice. We actually get to see what's happening. We get to see the distribution of all of the chunks in this shatter. Again, we can go in and move our pig head up and rotate it. There we go. And if you want to change the orientation of your handles, you can right click on it, say align handle, and say I'm going to align it to the world instead of the object, and I can change that back anytime I want. So this time we're going to turn it into an RBD glued object. So with the object selected, we're going to click on this third button in. And what this actually does is, firstly, it has the ability to deal with this as a fractured object because it recognizes it's in multiple pieces, but then it's also trying to keep those pieces together with bonds that we create. You can kind of see these red wires here. If I turn to a wireframe and kind of zoom in, you'll see that all of these connections have kind of been made between all of our pieces. And that's what's going to try and hold this pig head together, denoted by this glue object. And you can see that we have all of that added in. Glue constraints down here, which has been set to a specific strength. And if that strength is exceeded by the force of impact, it will actually shatter apart. So if we kind of press play now, we'll get a good idea of what's particularly happening. Cool. So we're getting some really interesting fractures here in that because the snout kind of hits first, all of that part of the pig head breaks apart. But because there's very little force when it reaches the back of the head, most of that's actually staying together. But the thing to remember is that this is actually still all fractured up. Again, if I kind of come back and visualize the pieces and then re-simulate, you'll see that it's not that those aren't fractured anymore. They are fractured. It's just that they're staying glued together based on the forces involved. So it's a really nice way of kind of getting that setup. Other things that we can do is add in our own static objects too. So we'll have a look at how to do that. So let's drop in a box object and dive inside, and we'll use a transform node to shape our object itself. So I'm going to change its scale in X and Z to maybe 5, and then Y to 0.2, and then in the Z scale, let's give it a 5 as well. So we have this kind of plank, and let's move it up and maybe off to the side, around about here. And what I want to do is take the pivot point and also move it backwards in space to this particular edge, and it's going to be half of that scale here. So that's going to be minus 2.5. Sorry, there we go. Oh, we're kind of getting some weirdness here. So instead of doing the scaling, I'm actually just going to do the sizing in the box itself. So 5, 0.2, and 5 here. There we go. So now our pivot point is in the correct position. Right, and what I want to do is have this actually rotate and spin round. I want it to be able to kind of hit our pig head. And instead of hand keying this, I'm actually going to type in a short expression of @frame with a capital F, and that will return the frame number that we're currently on. But if it rotates by 1 degree every single frame, it's going to take a very long time to spin round. So I'm going to multiply this by maybe 25 frames, by 25. So every single frame, it will rotate 25 degrees. And if I press play, you can see that that will automatically spin round for us. So we have it all set up and ready, but again, it is just polygons at the minute. So we need to turn it into a static mesh. And there's a couple of things on here. So it's going to be in our collisions tab. We can either turn it into a static object or use a deforming object that will kind of set us up. Say, we'll show the difference between the two. Firstly, we can turn it into a static object with it selected, and if we press play, and we'll see what particularly happens. Although it's rotating, you'll see that those collision objects aren't actually moving after it's hit. So let's kind of have a look at why. It's been added into our Autodot network here as a static object, and if we press play within our dynamics operator, then we can see that that object isn't actually moving. So that is the difference between static and a deforming object. If you have an animated object, you need to turn it into deforming geometry. And luckily, instead of using the other shelf tool, we can actually do it ourselves. So with those static objects selected, I'm going to use deforming geometry. And now if I press play, it will smash into our pig head almost on the second frame and send it flying into a million different pieces. So what we can also do is tailor our glue strength so that hopefully this initial hit isn't going to break it entirely apart straight away. So I'm going to multiply our strength by 10 just by adding a 0 on here and seeing what that particularly does. Well, we kind of get a little bit, but let's kind of double it again by going to 200,000. And what is actually happening is you can see it kind of happening. Most of it has broken off, but a good chunk of the head is actually staying together until it hits the ground over there. So if we kind of rewind it and press play, you can see the big parts of the head is actually staying together. It's only when it does get certain forces that it will kind of break apart. So it's really, really interesting kind of work, and always good fun to kind of shatter and kind of throw your objects around. Okay, so I think that's going to do it for this particular tutorial. What we will look at next is why we actually want to pack primitives, some of the additional speed ups that we can gain from that, and then we'll look at setting up a lot of this network ourselves manually, and how we can actually gain a lot of artistic control over rigid body dynamics. Okay guys, so stay tuned for more video tutorials. If you have any questions at all, please do get in touch. And if you have any requests for parts within Houdini that you'd like video tutorials on, then yeah, please send them my way, and I'll try and get some time to do them. Okay, thanks guys.